In this video, we are going to talk about how to solve optimization problems. Optimization problems are one of the common uses for derivatives. And so we're going to start by just talking about the steps to solve these. These are problems of finding like the maximum and minimum of some function. And so the steps to solve optimization problems. And so the first step is understand the problem by identifying important information as well as the function you want to optimize. So basically understand what you're even trying to do. Again, these steps come from a textbook, so the first step is a little on the nose. Step 2 is draw a diagram of the situation if possible. So it's very helpful to have a picture of the situation to kind of map out what you're actually looking at. Step 3 is introduce notation for all of the variables in the expression, in the question. Write the function you want to optimize as q equals something. And so we're just going to give a name of q to the thing we're going to optimize so that we can refer to it later. And then step 4 is express q in terms of the other variables. So typically you do this at the same time as step 3, but this is actually writing down some equation that tells you how is q dependent on the other things that you know about. Step 5 is if q is expressed in terms of more than one variable, then use given information to replace all but one of the variables in Q using equations. And so we did this in related rates problems as well. Basically this is saying is we're trying to get rid of all of the variables other than one of them. And so we want to make q just be some function, q equals f of x, say, where we're going to write all of the other variables in terms of x using the information given in the problem. And then step 6 is use the closed interval method, first derivative test, or second derivative test to determine the value that minimizes or maximizes q. So in other words, we're just going to use methods that we've already talked about at that point to figure out the minimum or maximum. And so that's take the derivative, look at a closed interval with the critical numbers, things like that. Things that we have done in previous videos. And so we're going to do some examples of actually going through this process. In terms of actually doing this, step 5 is usually where most students get hung up on, and it's just literally getting all but one of the variables to disappear using equations. And we're going to see that as we go through these examples. And so the first example is we have a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He does not need fencing along the river. What are the dimensions of the largest possible field he can fence off? Okay, so in this situation, we've got this fence that we're trying to put up. We have 2,400 feet of fencing, and we're putting it along a straight river, and so our situation looks something like the following. So we've got this river down here that's a straight river, and we're building some fence along it, and we want to maximize the area that's enclosed by this fence. So I'm going to give some variables, so we're going to call this x, and this y. It is a rectangle, and so because of that, the two sides on opposite ends have to be the same. And so we know here that the area of a rectangle is given by x times y. And this is what we want to maximize. We want to maximize A. Okay, so that is like our Q quantity that we're trying to maximize. And we've expressed it already in terms of the variables x and y. So if you're actually going through with the steps we had above, this is like steps 1 through 4. I at least tend to do them kind of all at once with those steps. So the next thing we want to do is we want to somehow rewrite the expression for A so it only involves one variable. And so the way we're going to do this is we're going to eliminate the variable y. And so we want to rewrite this expression of x times y without y involved in it. And we're going to use the given information about the perimeter to do so. And so we know he has 2,400 feet of fencing. And so that means that if I take these three numbers, x, y, and x, so 2x plus y, that must be less than or equal to 2,400. Okay, because that's how much fencing he has, so he can't go over that amount. Now, if he doesn't use all of the fencing, it should be pretty obvious he's not going to make as big of a field as he could. And so we're just going to assume that 2x plus y equals 2,400. And if you're not using all of the fencing, you could clearly make a bigger field, just use more of the fencing. And then we have that y then equals 2,400 minus 2x, just solving for y. So this gives us a relationship between x and y. And we're going to use that relationship to rewrite the equation for A in terms of just x. So we know A equals x times y, but y equals 2,400 minus 2x. And so we can rewrite A as 2,400x minus 2x squared. So this gives us a relationship now only dependent on x for the value of a. And so this is the step 5 that we were talking about before. And so it's just rewriting the thing we were trying to find the maximum or minimum of in terms of one variable. So now that we are in terms of one variable, the next thing we want to do is to figure out, using the closed interval method or some other method, what the maximum is. So we're going to first talk about some bounds. So we want to bound x. Well, x cannot be negative. The reason for that is we're building a fence here, and we can't have a negative amount of fencing, so x has to be greater than or equal to 0. But because we only have 2,400 feet of fencing, the largest x could possibly be is 1,200, because there are two x's showing up, and so if they were both 1,200, that would use all of the fencing and we'd have no width. Which obviously that's not going to be the maximum area, but that is another bound. So those are bounds on x. And so we have this closed interval of 0 to 1,200, and so we can use the closed interval method then to find the maximum. And now it's pretty clear it's not going to be at one of the endpoints, because 0 and 1,200 clearly not going to give the maximum area, but the closed interval method just tells us the maximum has to be at an endpoint or a critical point. So now we're going to find the critical points. So to do that, we're going to take our equation for a and take its derivative. So the derivative of 2,400x minus 2x squared is going to be 2,400 minus 4x. Remember, critical points happen when the derivative doesn't exist, or is 0. 2,400 minus 4x always exists, so we're just going to set this equal to 0. So we get 2,400 equals 4x, so x equals 600. And so 600 then is our critical point. So we have here our critical point of 600. And now the closed interval method tells us that the maximum happens at either an endpoint or a critical point. And so plugging these in, we have a of 0, a of 600, and a of 1,200. And if you plug in 0, hopefully it's obvious that if x is 0, the area is 0. And we mentioned before, if you plug in 1,200, you also get 0. Now, if you plug in 600, you get 2,400 times 600, because we're plugging it into a, remember. That's why I'm actually plugging it in, just so you can see what value we get out. So we get 2,400 times 600 minus 2 times 600 squared, and this equals 720,000, I mean. And so the maximum area that we could possibly get is going to be 720,000 feet squared. But what we actually cared about was we cared about the dimensions. So it's helpful to remember what the question asks. The question did ask, what are the dimensions of the largest possible field? And so we know that x is 600. Now y is 2,400 minus 2x. So this is 2,400 minus 2 times 600. So we get 2,400 minus 1,200. So we get 1,200. So y is 1,200. And so the fencing's dimensions is then going to be 600 feet by 1,200 feet. And so those are the dimensions of the largest possible field that this farmer can put up with his 2,400 feet of fencing. Okay. So now let's move on to another example. And so here we have a cylindrical can is made to hold 1 liter of oil. We want to find the dimensions of the can that will minimize the cost of metal, assuming all the metal used is the same cost. Okay, so you could technically complicate this if you said like the bottom and top cost more money than the sides or something like that. We're just going to assume all of the metal used is the same price to make. That is pretty standard in constructing cans, so that's not really a big assumption. So what we've got here is we've got a cylindrical can. So if we draw a can of oil, we've got this can of oil that we're creating, and its volume is going to be 1 liter. And we're trying to figure out how to minimize the cost of metal. And so if we're trying to minimize the cost of metal, the amount of metal needed is the surface area. So we're really trying to minimize the surface area because we want to minimize how much metal we need since all the metal costs the same amount. So we want to minimize the surface area of the cylinder. So let's put in some notation so we can actually define what the surface area is. So we're going to let the radius of the can be r and the height be h, kind of like we normally do for a cylinder. Now you probably do not know what the surface area of the cylinder is. If you do though, that is great. We're going to talk about how to find it. And so the way you find it is there are 2 pieces of the top and bottom. So we have the top here and the bottom here. We are assuming a paint can does have a top, or an oil can has a top to it. And so we've got 2 pieces that are the top and the bottom. And each of these is going to have a surface area of just the area of a circle. And so remember, the area of a circle is pi r squared, but we have 2 of them. So we're going to have 2 pi r squared making up from the top and the bottom. But then we also have the part that's wrapping around. To see what we're doing there, we're going to do the trick of thinking of cutting a can along the side and then unraveling it. And so if you think of actually taking a cylinder and cutting it along the side and then flattening it out, you actually get a rectangle. And so we're going to get a rectangle, and now the height of the rectangle, I'm just picturing that I've actually flattened out this piece. So the height of this rectangle is going to be h, because that's this distance right here. And now we need to consider how long is the side. Well, the side is coming from the part that's wrapping around. And so the side is going to be like this length that goes around the circle, because that's when we unwrap it, that becomes this long side. That becomes this side. And that is going to be the circumference of the circle. The circumference of the circle is 2 pi r. And so this length here is going to be 2 pi r. So the whole area here is 2 pi r h. And so we have these 2 pieces from the top and the bottom, each with pi r squared area. And then we have the rectangular part with a 2 pi r h. And so the total surface area is going to be 2 pi r squared plus 2 pi r times h. And so that's just coming from just what we barely did. So now this is our surface area. This is what we want to find the minimum of this time. But notice we have 2 variables again. We have r and we have h. So what we're going to use is we're going to use the fact we know the volume of our can to get a relationship between r and h. And so we call that the volume of a cylinder is equal to pi r squared times h. And so we know that the volume is 1 liter, but we measure distances in centimeters, not liters. So we're going to convert 1 liter to centimeters. 1 liter is 1,000 centimeters cubed. So we're going to have 1,000 equals pi r squared h. And that's just from the fact 1 liter equals 1,000 centimeters cubed. That's just so we have normal units, we don't have weird units going on. And so now we're going to solve for h because it's the easier one to solve for. So h is equal to 1,000 divided by pi r squared. So that gives us a relationship between h and r, and so we can now replace h in our formula. And so our surface area, which I'll write as SA, is going to be 2 pi r squared plus 2 pi r, and it was h, but h is 1,000 divided by pi r squared. And so this then gives us our equation involving only r. Now if we multiply this out, you get 2 pi r squared plus 2,000 divided by r. Things cancel. So the pi here cancels with this pi, and r cancels with one of the r's there. And then 2 times 1,000 is 2,000. So this is then our equation that we want to find the minimum of. And so from this, we're going to take the derivative and do everything like normal. Now we know r is not going to be 0, because if the radius was 0, that's not going to form a can. So the fact we're dividing by r here, it's not an issue. So let's find the derivative now. And remember, we'll find the derivative, we find critical points. We're looking for where the minimum can occur. So taking the derivative, we have 2 pi r squared's derivative is going to be 4 pi r minus 2,000 over r squared. Remember, the derivative of 1 over r is negative 1 over r squared. So that's why we get negative 2,000 over r squared. And then this then becomes 4 pi r cubed over r squared minus 2,000 divided by r squared, which is then going to be 4 pi r cubed minus 2,000 divided by r squared. I'm just rewriting it like this because we want to figure out when this is 0, and it's going to be easier to have them combined. And so we want to know when this is 0, so we're going to set 4 pi r cubed minus 2,000 divided by r squared equal to 0. Since r squared is not 0, we just really care about when is 4 pi r cubed minus 2,000 equal to 0. So that's going to be when 4 pi r cubed equals 2,000. Pi r cubed is then going to have to be equal to 500. So r cubed is equal to 500 divided by pi. And then we get r is the cube root of 500 over pi. And so that then tells us that the cube root of 500 over pi is our critical point. Okay, so we have our critical point of the cube root of 500 over pi. But now we need to know, is this giving the minimum or the maximum? And we don't have a closed interval here. We know r is positive, but we don't really have a cap on what r could be, because if you make r wider and wider, you can just keep making h smaller and smaller. So you could make a can that had 1 liter volume with a ridiculously large value for r. Now in practice you wouldn't do that, but you could. And so what we're going to do is we're going to use the idea of increasing and decreasing. So if you remember the first derivative test, that told us when we could find local minimums and maximums. But it also can help you find absolute minimums and maximums. And that's what we're going to do here. So we're going to create a sine line. And what we're going to do is, this is like the table that we used before. And so we're just going to look at the values below the cube root of 500 over pi and above the cube root of 500 over pi. And so if you plug in a number smaller than this, you might not know a number smaller than this, so I'm just going to plug in 1. 1 is smaller than it, and 500 is clearly larger than it. Okay, and so we're just going to check the sign of things. So this is just like the table that we did before. If you think of the table from before, we're like looking at the interval 0 to the cube root of 500 over pi, and then the cube root of 500 over pi to infinity. So we're just like creating the interval and like we did before, and then our test point is 1 and 500. And then we care about the sign of things. Now we're plugging them into the derivative, which remember the derivative is this expression up here, ignoring the 0. If you plug in 1 here, you're going to get 4 pi times 1 minus 2,000 divided by 1. And that is clearly negative. So this is clearly less than 0. And if I plug in 500, I'm going to get 4 pi times 500 cubed minus 2,000 divided by 500 squared. And now, I don't know exactly what that is, but that is clearly greater than 0. Okay, you can actually compute it with a calculator. I just didn't do that ahead of time. But really all we care about this is the sign. So what this tells us is for every value below the cube root of 500 over pi, the derivative is negative. So it's decreasing everywhere up to the cube root of 500 over pi. Then it's increasing everywhere after that. And so that means we must have a minimum at the cube root of 500 over pi, but it has to be an absolute minimum because we're always decreasing before and always increasing after. And so you can kind of think of it, it kind of looks like a parabola in that the cube root of 500 over pi is this bottom piece of the parabola. It might not exactly look like a parabola, but it sort of takes on that appearance. And so that tells us that that has to be where we have a minimum, and it has to be an absolute minimum. So R equals the cube root of 500 over pi corresponds to an absolute minimum. Okay, now we wanted to know the dimensions, so we need to know all h as well. So h was equal to 1,000 over pi r squared. So this is going to be 1,000 divided by pi times 500 over pi to the 2/3. So I'm taking the cube root of 500 over pi and then squaring it, which is the same as the 2/3 power. And this equals, if you simplify it, 2 times the cube root of 500 over pi, which is 2 times the radius. And so the dimensions then are going to be a radius of the cube root of 500 over pi and height of 2 cube root of 500 over pi. And so those are the dimensions then for our can of oil that'll minimize the cost of making it. So next we're going to look at one more example. And so this is a pretty common example in math classes to talk about. So what we want to do is we want to find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Okay, so if you draw a picture of what's going on here, the parabola y squared equals 2x looks something like this. We've got some point here. I'm just going to draw it at a random spot, 1, 4. And we want to find the closest point on the parabola to this point. So it's going to be like right here. Okay. And so the way we can find any distance, though, is using the distance formula. And so you may or may not remember what the distance formula looks like. And so this comes from the Pythagorean theorem. You can think of actually dropping like a straight line down, and then we're forming a triangle where our distance here is our length there, and then this is just the difference in y coordinate. So this is like delta y, and this is delta x. So the change in y and change in x is the way you can kind of see it. And so the distance formula in general, it's coming from that what I just said with the triangle, but in general the distance between x1 comma y1 and x2 comma y2 is d equals the square root of x1 minus x2 squared plus y1 minus y2 squared. And again, this is just coming from the distance formula. If you take your 2 points, it's coming from the Pythagorean theorem. The distance is this line right here, d, and so what you do is you draw a triangle. The length here is going to be x2 minus x1, and this is going to be y2 minus y1. And then from the Pythagorean theorem, you get what d equals. So that's all we're doing to get the distance here. So now we want to find the distance between the point 1, 4 and a point on the parabola. Well, every point on the parabola has the form y squared equals 2x. That's the equation of the parabola. So solving for x, we get that x equals y squared over 2. So every point on the parabola looks like looks like y squared over 2 comma y. Every point on the parabola is going to look like that. And so we're going to plug that in for a point on the parabola, and then our other point is 1, 4. So the thing we want to find the minimum of, we want to minimize the following. So it's d equals the square root of the x-coordinate, which is 1/2 y squared minus 1. It's the distance between the point y squared over 2 comma y and 1, 4. So we have 1/2 y squared minus 1 squared plus y minus 4 squared. And that is what we want to minimize. And notice it only has one variable in it. It only has y in it, so we don't have to replace a variable. That's kind of what we're doing here in replacing a variable. But when it comes to the distance formula, it's a little annoying because there's a square root in it, and so when you take the derivative, it makes things a bit more complicated. And so what we do is we use the following fact. At least we're going to use this fact here. And so the place where d has a minimum is also where d squared has a minimum. Okay, so wherever d has its minimum at, meaning the y value that minimizes d, will also minimize d squared. Okay, so this comes from the idea that a is less than b gives that a squared is less than a times b, which is less than b squared. And so a is less than b if and only if a squared is less than b squared. So we're going to look at d squared, and that's going to be the thing we're actually going to take the derivative of. So d squared is going to be equal to the function f of y, which equals 1/2 y squared minus 1 squared plus y minus 4 squared. So now this is what we want to take the derivative of. So we're going to do that. So we have f prime is equal to 2 times 1/2 y squared minus 1 times the derivative of 1/2 y squared minus 1 plus 2 times y minus 4 times the derivative of y minus 4. Multiplying this out, we get 2 times 1/2 y squared minus 1. The derivative of 1/2 y squared is just going to be y plus 2 times y minus 4 times 1. So this then, if we multiply it through, is going to give us 2 times 1/2 is just 1. So we're going to get y cubed minus 2y plus 2y minus 8. So we get y cubed minus 8. So we've got y cubed minus 8, and we want to know when this is 0. So we're going to set this equal to 0. So y cubed minus 8 equals 0. So y cubed equals 8. So y equals the cube root of 8, which is 2. So our y value is then 2. And then using the sign line like we did before, plugging in things. If we plug in 1, we're going to get 1 minus 8, so we get 7. Or get 1 minus 8, which is negative 7, which is less than 0. If we plug in 3, we're going to get 27 minus 8, which is 19. And that's greater than 0. And so we see that 2 is indeed where the absolute minimum occurs. And so the absolute min occurs at y equal to 2. And so figuring out what the x value is, we have x equals 1/2 times y squared, so times 2 squared, which is 1/2 times 4, which is 2. And so the closest point to 1, 4 on the parabola y squared equals 2x is the point 2, 2.